So working with a phasor diagram can be one of the most important to understand. Still, on your AC circuits, which is the parallel RLC circuits, you can be given a phasor diagram that you need to study and see exactly what is happening on the phasor diagram that you're given. From this phasor diagram, we are given to study it, and that is to consider the phasor diagram in Fig 2 on the attached diagram sheet to determine the following from the phasor diagram, the supply frequency being 50 Hertz. We have got our phasor diagram, if you take it's on top, indicating that the current across the capacitor is bigger than the current across the inductor. The current across the capacitor is bigger than the current across the inductor. Working with the currents, that means we are talking about a parallel RLC circuit. This is a parallel. Whenever you're working with the currents, they can give you a condition where you are working with the reactances, XC, XL, that part, when given in form of a phasor like this, where you're given XL minus XC, that one, it is for an RLC in series. When given currents like this, it's in parallel, so not about that. So remember, your normal parallel RLC circuit, how it operates. The normal parallel RLC circuit, where you understand that the voltage is the same throughout the current, which is the total current, is the phasor sum of these currents that we are given. That idea is the same. So that is the same thing that we are having in this, but only they presented it on a phasor diagram, where the total voltage is given 110, that is 100 volts. The current across the resistor, that is the current across the resistor, which is 2 amps. That one across the capacitor, which is 3,142. The current across the inductor, which is given as 2,122 amps. We're given all these currents. Something that we are used to. But only that they are drawing on a phasor, but it was supposed to be like this. It was supposed to be the parallel current. You're given currents. That's a parallel. All right. So the question is 3.11. Calculate the value of the inductor in millihenries. 3 marks for that. The value of the inductor. So if we're to determine the value of the inductor, we've got a parallel circuit where we understand that the voltage is the same. Remember, I talked about this, that in a parallel circuit, voltage is the same. So we can calculate the reactance across the capacitor, across the inductor, since this is the inductance. So you can calculate the reactance across the inductor from 2 pi FL. Remember, that's 2 pi times the frequency and the inductance. We do not have. Guys, this is what we want. This is what we want. Sorry for that, guys. This is what we want. Remember, we want the inductance. See the disadvantage of not writing what you need. All right, we want to calculate the inductance there. So, like I said, XL is or can be calculated from 2 pi FL. So you can make L the subject, divide by 2 pi F, divide by 2 pi F. So that means inductance is given as XL over 2 pi F, but we do not have XL. So to determine XL, we can take advantage that it's a parallel combination where voltage is the same. So you can divide by the current across the inductor. The voltage of 100 volts divided to the current across the inductor. That's 2,122. So that means we've got XL, which is going to be 47,125 ohms. So with the reactance across the inductor, we can substitute this that is 47,125 over 2 pi times the frequency. Remember, the frequency is 50. So this will give us the value of the inductance, since they are told in millihenries. So in millihenries, we are going to multiply by the opposite, which is 10 to the exponent of 3. Our answer will be automatically in millihenries. So that was going to give us the value of the inductance, which is 150,004, which is in millihenries, or you can just write as 150 millihenries. That is the idea there. You can work from the phasor, analyze the phasor. Is it for a parallel or a series? Okay. 3.12, the value of the capacitor in microfarads, 3 marks for that. All right, so again, just like the previous case, we're going to need XC from V over, so meaning to say this time we are going to have our XC as V over IC. So it will be V over the current across the capacitor. We have got the current across the capacitor. The voltage does not change. Current across the capacitor 3,142. So that was going to give us XC, which is 31,827 ohms. With this, we can calculate the value of the capacitor. Remember, our XC, the formula from our formula sheet, we are also given XC is equal to 1 over 2 pi FC. And I talked about this, that if you want to calculate the capacitor, just interchange with C. So capacitance is equal to 1 over 2 pi FXC. Just interchange these two. So you're going to substitute these values that we are given. That is 1 over 2 pi times the frequency, which is 50 hertz, times the reactance of the capacitor, which we calculated, that's 31,827. So since you are told to write this in microfarads, so we are going to multiply by 10 to the exponent of 6. This automatically converts our answer to microfarads, meaning to say whatever that you are going to have on your calculator is in microfarads. Whatever that you're going to obtain will be automatically in microfarads. So this is going to be 100,013 microfarad, or just 100 microfarad. Just like that. We were not having a circuit. We're given a phasor diagram. Guys, the supply current from these currents that we are seeing, remember, the current is the phasor sum that you're supposed to consider. When working with the current, you work with the phasor sum, so you're supposed to compare between the currents that you're given across the inductor and the capacitor. Which one is bigger? The current across the capacitor is bigger than the current that we are having across the inductor. IC is greater than IL. So it means on our formula for the parallel circuit where we are calculating the current, it is supposed to be IC minus IL, because it's the bigger value that we are having IC. So I said this formula is going to be now the total current is the square root of IR squared plus the difference between these two, that is IC minus IL squared, since the capacitor is the one that is bigger than that of the inductor. These currents are given. Remember from your phasor diagram, these currents are there. The current across the resistor, that is 2 squared, plus that of across the inductor, the capacitor, 3,142, minus the current across the inductor, the capacitor minus that across the inductor, which is 2,122. That's 2,122. Then everything in this bracket, you're supposed to square it. You square everything in that bracket. So this is going to give us the total current of the circuit, which was going to be 2,245 amps. That is what you're going to have. Just like that. Then the phase angle on 3.14, the phase angle that is 2 marks, and I said in a parallel combination whether you are stuck, you do not know anything. These formulas are for a parallel combination. You can just take this one. Phase angle, it is arc cos IR over IT. The current across the resistor over the total current. So from that formula, we can calculate our phase angle. Remember, we calculated our total current. So it means we can have our phase angle from there, taking the current across the resistor. Theta is equal to arc cos, so that's 3.14. Theta is equal to arc cos, the current across the resistor over the total current. That is, theta is equal to arc cos, the current across the resistor, as we are given, that is 2 amps, which is IR. That is 2 amps. So as long as you're dealing with a parallel circuit, that is the formula that you have from a formula sheet that you can take. There are so many formulas, but I advise you that you use the formulas that you're given from the formula sheet, because at the end of the day, that is the only assistance that you have. That is the only friend that you have in exam. There's no one to tell you a formula. So in a parallel circuit, these are the formulas, all right? You can use this one where you have to relate again to that part. But this one is straightforward. There's nothing that you're relating. IR and IT already have. If it was a series circuit, the phase angle from arc cos R over Z, these formulas, you won't go wrong because you'll be having those, or you'll be having those values automatically. You'll be having those values. So that is theta. It was going to give us 27,017 degrees to 3 decimal places. That is what we're going to have at the end. So these are the typical questions that you might be given working with the phasor diagram to interpret a phasor diagram as if you were given a normal circuit. As if you were given a normal circuit, but you are interpreting a phasor diagram. It can be like that. So these are your typical questions that you must also consider as you are revising. So that's it, guys. Till we meet again.